Hello everyone, I'm Chuanbin Zhu from GFZ. Today, I'm going to talk about a novel amplification of earthquake HVSR in site-specific amplification estimation. First, let's have a look at a surface and downhole recording pair, one recording station at a ground surface and the other in a borehole. Then we can have the horizontal to vertical spectral ratio on the ground surface HVSR, as well as the horizontal to vertical spectral ratio at the downhole HVSR-B. On the other hand, we can also have the surface-to-borehole spectral ratio in the horizontal direction SBSR and the surface-to-borehole spectral ratio in the vertical direction SBSRV. And this is the expression of surface HVSR, and which equals to HVSRB over SBSRV multiplied by SBSR. Let's first have a look at this term, HVSRB, the HVSR at bedrock site. This figure shows the empirical results of HVSRB for many KiK-net downhole stations. So it shows that the HVSRB is very close to 1.0 in linear scale over a very broad frequency range. So we can assume HVSRB is close to 1.0 and then substitute this equation into the first one. And then we can have this formula. SBSR equals to HVSR multiplied by SBSRV, and which means the horizontal amplification is the product of surface HVSR and the vertical amplification SBSRV. So in order to have the horizontal amplification, we need to multiply the surface HVSR of a given site by its vertical amplification. This equation explains why HVSR underestimates the horizontal amplification. That's because of the presence of the vertical amplification, which is very prominent in relatively high frequency range. So to get the horizontal amplification, we need to correct surface HVSR of a given site by its vertical amplification. However, in a forward amplification, we might have surface HVSR, but we do not have the site-specific vertical amplification. Motivated by the work of Kawase, we propose to use generic vertical amplification spectrum in this equation to get an approximation of the horizontal amplification, P-SBSR, which means pseudo SBSR. We will compare this P-SBSR with the actual SBSR later on, but first I want to introduce you how we get the generic vertical amplification spectrum, namely the correction spectrum. Firstly, it's data selection. We selected our ground motion data from a processed database by Dawood et al. 2016. These are our data selection criteria. After the initial data selection, we have another round of data selection. I will explain why we have a second round of selection by using the Ghana Valley downhole array. And this array is unique in that it has many downhole sensors at different depths. The surface station, downhole station number 1 to 5 at depth 6, 15, 22, 50, 150 meters respectively. So we can have the ratios from surface to different downholes, SBSR01, SBSR02 in respective figures. To better compare them, we plot all these curves in one figure down below here. And from this figure, we can see that the SBSR01 or 02, 02, 03, 04 significantly underestimate the curve SBSR5. So this means that neglecting deep velocity variation causes a considerable underestimation of set responses at not just the low frequencies, but surprisingly also high frequencies. Since we use SBSR as a benchmark in this study, and SBSR just represents the set response of the soil column between surface and downhole sensors. So if a site has a deeper velocity contrast beneath the downhole sensor, then the SBSR is not a full representation of the empirical set response at that site. To avoid that, we further select our site to exclude those with deeper velocity contrast below downhole sensors. We can have a look at these two sites, one on the left with velocity contrast below downhole, and the other on the right, which is considered to have no deeper velocity contrast below downhole sensor. And for this site, there is no deeper velocity contrast. The HVSR and SBSR will coincide with each other in the relatively low frequency range. And whereas on the left-hand side, the site having a deeper velocity contrast, there is a clear peak on its HVSR in relatively low frequency range. But this peak is completely absent on its SBSR. So this means there is a deep velocity contrast below the downhole sensor, and this deep velocity contrast is not captured by SBSR. So based on this, we define a site as having a major velocity contrast below its borehole if there exists a frequency at which HVSR amplitude exceeds SBSR value by 20% or more. So based on this criteria, we have further selected 90 KiK-net stations. And then we used k-mean clustering to further classify these 90 sites into 5 categories. And then we can have the average vertical amplification for each category. Next, we use this predefined vertical correction spectrum, namely the vertical amplification spectrum, to correct our HVSR, then to get the pseudo SBSR. On the other hand, we compare the performance of this empirical correction to HVSR with the widely implemented ground response analysis, TTF, in reproducing the empirical amplification, SBSR. In the computation of a theoretical transfer function based on ground response analysis, we consider the arbitrary variability in velocity profile by randomizing about the base case profile. However, we did not consider the epistemic uncertainty by using up and lower range profiles, because previous studies have shown that the up and the lower range profiles fail to reproduce some site signatures like resonant frequency. And these figures show an example of the comparison between correct HVSR, namely the PSBSR, with theoretical transfer function using SBSR as the benchmark. We can see that the correct HVSR is much closer than the original HVSR to empirical transfer function. And to quantitatively assess the goodness of fit between any two spectral ratios, we use different metrics, Pearson's correlation and Spearman's Zhou-Kandos-Tau index agreement D, and one absolute measure, the mean absolute error. These are the histograms of different goodness of fit measures. The blue one represents the results for correct HVSR, namely PSBSR, whereas the red ones represent results for theoretical transfer function from ground response analysis. No matter which goodness of fit metrics we use, it's very obvious that the correct HVSR achieves a much better match with empirical transfer function than theoretical transfer function from ground response analysis. And this table gives the percentage of sites with a good match for each method, and we use different definitions of a good match. Regardless of the definition of a good match, the correct HVSR has a much higher success rate than the theoretical transfer function in reproducing the empirical transfer function. So our take-home message is that the empirical correction to HVSR is highly effective and achieves a good match in both spectral shape and amplitude at the majority of the 90 KiK-net sites, as opposed to less than 1/3 for the 1D SH modeling. In addition, the empirical correction does not require a ground model as the ground response analysis does, and thus has a great potential in site-specific seismic hazard assessments.